so it starts out with chapter P. So chapter P is kind of just a preview of what we're going to do in calculus. All right, so there's two classic problems on every AP exam and every calculus class in general. Okay, so the two types of questions are about slope, so about a tangent line touching the curve, and the second one is about finding the area under a curve. So we know how to find areas of things like triangles and circles, but what if it's like the area under a parabola, right? Kind of strange. So we use calculus to solve those types of problems. Okay, so the first tangent line problem that we're going to do, it says, for example, find the equation of the tangent line to y equals x squared at the point 2, 4. Okay, so let's kind of sketch out what we're talking about. Okay, so you have y equals x squared, and you have some point 2, 4. And you have a tangent line. The tangent means touches, so it's barely going to touch the curve at that particular point. So at 2, 4. It's coming down and it's just touching. All right, so we need to be able to find the slope of this tangent line. So back in the day, when calculus was first created, they did something a little bit tricky. They couldn't just find the slope of a line using 1 point. We know that we can find the slope of a line using 2 points. So they took 2 points. So they took a point that was really, really close to 2, 4, so maybe 2.5, comma, something. And they connected those 2 points with a line. Okay, and this is called a secant line. Secant line. And then they took that 2.5 point and they split it closer and closer and closer until it was almost exactly on the point 2, 4. Okay. So they found the slope between 2 points that are kind of far away, and then they moved the points closer, moved them a little closer, a little closer. So that's what we're going to do. Okay, so first we need to find the y value associated with 2.5. Okay, so go ahead and get out your calculator. We're going to use this table function on that calculator. So under y1, that y equals, you're just going to put in x squared. And then you're going to go to the table. So you can do second graph, which is table. All right, and hopefully your graph is set up so that you can put in whatever values you want. Can you guys put in 2.5, like enter 2.5? Okay, if you can't, then what you need to do is go to table set. Okay, so that is under window, so the second window, table set. And it's going to say independent, and you want to set it to task. So go over to task. Okay, so under y1, we have x squared. You're going to go to table. And now you can just put in whatever values you want. So if I put in 2.5, it's going to give me what 2.5 is squared, which is 6.25. Does that make sense? Okay, so we're going to fill in these values in for the y. So that's our first point. Our first point is 2.5, comma, 6.25. So over here was 6.25. All right, now I do 2.1. So this is just a quick way of doing two tables, right? So 2.1, now I get 4.41. And then do 2.01. So you get 4.0401. Now I want to make sure that that was my entire number. So what you can do is you can arrow over. So arrow over under y1, so you have x and you have y1. So where it says 4.0401, you can highlight it and you can get on top of it, and then below it says 4.0401. Okay, that's telling you that that's all the digits. Now put in the next one, 2.001. Now it looks like it's going to cut off a little bit. So if you highlight the number, you can get all the digits, so 4.004001. You see writing that out. So it's not showing all the digits for that one. So if you go over it, if you highlight over it, it will show you the rest below. So you're seeing a pattern. So 4.00040001. So there's definitely a pattern. So each additional zero you add in, you get another zero in between the fours. Okay, so those are points. Okay, so now we want to know the slopes joining these points. Okay, Okay, so this is going to be a little bit harder, so I'm going to write out the first couple. Okay, so if I talk about the slope of the one that's 2.5, now remember this is the x value of the point, so remember that's really the point 6.25, like 2.5 comma 6.25. You want to write the y value, or you just notice that they're all up above. All right, so we do slope by changing y over changing x. So I'm going to go between p and q. All right, so if I go between p and q, so I'm going to have 6.25 minus 4 over 2.5 minus 2. Okay, and let's go actually and just find this on our calculator. So I'm going to do 6.25 minus 4 in parentheses divided by parentheses 2.5 minus 2. Okay, so I put this in like this on the calculator on the main screen. Okay, and when I do that, I get 4.5. So I'm going to put in the slope as 4.5. Okay, and some of you guys have fancy calculators where you can just arrow up and you can edit the equation that you had before. Some of you don't, though. Okay, so how many of you guys can just arrow up and edit? Yeah, a couple of you guys can. If you can't, then do second enter, and that takes the last entry that you have and you can edit it. So now let's do, so instead of doing 6.25, I'm going to do 4.41 minus 4 over 2.1 minus 2. So I just edited it. Okay, and that's the second slope, so that's going to be 4.1. And then do the next one. So you can insert numbers. Minus 2.01. All right, I get 4.01. Are you noticing a pattern? How's it related to the x value? So 2.5 gives me 4.5, 2.1 gives me 4.1, 2.01 gives me 4.01. It's always just 2. So 4.001, 4.0001 is All right, so there's a reason. So it says, well, what do you predict the slope at P is? So at the point P, so at exactly 2.4 point P, or 2.4, what is the slope going to be? 4. It's getting closer and closer to 4. Does that make sense? And the slope is going to be 4. All right. And it says, use this to find the equation of the tangent line of y equals, let's see what I have. Y equals x squared at the point 2, 4. All right, so I'm going to have my slope is 4, and my point is 2, 4. So my equation of my tangent line, I'm going to use my point slope form. Do you guys remember this form from Algebra 2? Point slope form. Now this is really important in AP Calc, and I think it's before. All right, because if you just write it in this form, that's your answer. You stop right there. But let's say you had gone further, so don't write this down. And let's say I was doing this math and I was like, okay, y minus 4 equals 4x minus 8. And then I know I have my minus 4, so I'm like, oh, 4x minus 12. And I made a typo. You guys understand what I'm saying? Like I meant to add 4 to both sides, but with the stress of the AP test, like proving that stuff. All right, I wrote the wrong thing. You get the whole point wrong then. You missed the answer. Even though you had it right here. And it's like, wait, I had the answer. Okay. Yeah, it's me, isn't it? So you have to stop there. So go ahead and stop at the point slope form. And, you know, I thought that was kind of dumb. I learned that in an AP conference a couple years ago, and I was like, this is dumb. And then I was like, I'm not going to tell them that. I can just go all the way down. And then I noticed that people do make that mistake all the time. If they mess up, like going through these forms. And I don't know what it is. Maybe it's just like your environment, you get stressed. I don't know, but I've seen that a lot of people make that mistake. So leave it like that. Okay, so it says calculus isn't always going to be the time consuming. So you're not going to have to find the slope at a particular point by doing all these approximations. Okay, this is kind of the background information that's leading up to what we're going to talk about in chapter 1. It's just called limit. Okay, so a limit is as you get closer and closer to a certain value, what happens. Okay, so next up. So another common situation in calculus is the area problem. So it says, for instance, approximate the area under the curve y equals x squared between x equals 1 and x equals 3. So this is what I was talking about. Like, we know how to find the areas of triangles, of rectangles, of circles. We don't know how to find the area under a curve like this. Okay, so what we're trying to find is this little piece right here. So when I say under the curve, it usually means trapped by the x-axis. Okay, so it says in order to do this, I choose several x values between these 2 points. So we're going to keep things simple, and we're going to use x equals 1. That was right here. X equals 1.5, x equals 2, x equals 2.5. So we're using all these. So we're using these points along the curve. And we're going to draw overestimates and underestimates. So how can you approximate an area? What shape could you use? You can use triangles and rectangles. So I think Isaac is saying like you could do a rectangle here and a triangle here. Okay, we're going to make this really easy though, and we're just going to use rectangles. So I'm going to do what's called an overestimate and also an underestimate. Okay, so let's start with the overestimate. Okay, so I want all of my rectangles to overlap the area that I'm trying to find. Okay, so I'm also going to use x equals 3 here. All right, so what I'm going to do is I'm going to use what's called right-handed. So I'm going to take my right hand, and I'm going to draw on the point, and I'm going to go straight over to the left. So start with your right and move to your left. That's called right-handed. All right, and that's a rectangle. All right, and then I'm going to start with the right and move to the left. That's a rectangle. Start with the right and move to the left. That's a rectangle. Does that make sense? Okay, that's going to be my overestimate. Okay, so I need to know the height of these rectangles. You guys know the width of the rectangle? 0.5, right? So the widths are all 0.5. Okay, but my heights, I don't know. So how do I find this first height? This one right here. Any guesses? How do you find that y value that's on the curve? Plug in that point, right? So you're plugging in 1.5, so you're doing 1.5 squared. All right, so you can go back to your table since you already have it. You can do 1.5 squared. Hopefully you guys know what 1.5 squared is. So 2.25. All right, how about the next one? Okay, well now that's at 2, right? So 2 squared is going to be 4. The next one is 2.5, so 2.5 squared is 6.25. And the last one was 3 squared, which is 9. Okay, those are the heights. My curve was y equals x squared. So you're plugging in whatever x value you're at. You're at x equals 1.5. Well, you can do it in the table. It's just your original function is y equals x squared. Yeah, so this is 1.5 for my x value. This one was 2. Yep, you got it. All right, so my overestimate is going to be the first rectangle has a width of 0.5 and a height of 2.25. The next one has a height or a width of 0.5 and a height of 4. The next one has a width of 0.5 and a height of 6.25. And the last one has a width of 0.5 and a height of 9. Now you're going to make this easier on yourself, and you notice that they all have common width. They all have 0.5, so pull that common width out. So you're going to have 0.5 on the outside. And you're going to have 2.25 plus 4 plus 6.25 plus 9. So you pull out the common factor. So go back to your main string and let's find that. Did you guys get 43? 0.5 is the common width for all of them, so you can pull the 0.5 out. Now you guys can get fancy and use other colors if you want. You guys want a colorful color? Oh, did I get something? What did I do? Oh, I divided by 0.5. Man, I know. So 21.5 times 0.5. So 10.75. That was big. All right. Eric gets 1 point. All right, so I have 10.75. All right, so now let's do the underestimate. All right, now I want rectangles that are under. I'm talking about color pencils in case you want to use the color pencil. Some people like to keep their notes like color coordinated or whatever. All right, so an underestimate. So each time I have my rectangle, it's going to go under what I wanted. It makes sense. It's not going to totally cover what I want. So my underestimate, I'm going to use what's called left-hand endpoint. Okay, so imagine taking your left hand and moving towards the right. It makes sense to start with the left and move to the right to cover it. Okay, so that's going to be here, 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 and here. You guys see what I'm saying? Let's go on there and so you can see. Okay, so your underestimate, the first little green, the green rectangle that I have has a width of 0.5 and a height of what? What's the first height? I didn't draw it before. 1, right, because it was 1 squared. So height of 1. The next one has 0.5 and a height of 2.25. The next one has a width of 0.5 and a height of 4. And the last one has a width of 0.5 and a height of 6.25. Why did I not use 9? Yeah, 9 is past that interval, right? It's past since we're using everything on the left. You see how this works? Left endpoint to use the things on the left. 1, 2.25, 4, 6.25. Right endpoint to use the things on the right. 9, 6.25, 4. All right, so pull out the common factor to make it a little bit easier. So 1 plus 2.25 plus 4 plus 6.25. All right, so 1 plus 2.25 plus 4 plus 6.25. All right, and on this one you get 6.75. Okay, so what do you think a good estimate in general would be then? So what could you do with the over and the under? Yeah, so I would probably take 10.75 plus 6.75 and divide by 2. All right, so around 8.75 would be my estimate. The actual answer, so later on we'll learn how to do this with calculus, but the actual answer is 8 2/3. That is the actual area under that curve. Those are pretty close. You got 8.75 and we use 4 rectangles. So what do you think happens if we use like 10 rectangles or 20 rectangles? Yeah, it's going to be even more accurate, even more precise. Does that make sense? So we were pretty close to the actual answer, only using 4. Yeah. Well, that's a good question. So Santiago says, if you do an overestimate, do you use the last point always, like right endpoint? Okay. What if it had been like this? So what if my my parabola went this way and I wanted the area from here to here? Okay. Then the left endpoints would end up being overestimates, right? You see what I'm saying? So start on the left and go over. That's an overestimate. So it kind of the lowest point is every time. Yeah, you can do that one. So don't think of like left versus right. So just think, am I covering the entire curve? Now there could be some that are even harder. So I don't know about the lowest one on this one. What if I had a curve where it went up and then down again? Like overestimates, you're always going to cover. You know what I'm saying? So like maybe for some of it you use a right endpoint, and some of it you use a left endpoint. You kind of have to just draw off a rectangle to see what's happening. So it can be tricky. All right. And we do get to the point where we only use right or only use left. And then we are going to learn another one where we only use this. Okay, so we're going to learn lots of different calculations. All right, so let's try this one again. So let's do f of x equals the square root of x. Okay, so it says consider the function f of x equals the square root of x at the point 4, 2. Right, kind of hard to see 4, 2, which is right here. All right, and graph the secant line passing through x equals 1, x equals 3, x equals 5. Okay, so let's start with x equals 1. Okay, so if I have this secant line here, okay, that should be slightly below your curve. You guys see, slightly below your curve. All right, so let's find the slope of, and I'm going to kind of shortcut this. I'm going to write m1, so I remember it's using x equals 1. So don't forget. Okay, so remember that's the point 1, comma 1, because you're plugging into the square root function. So 1, comma square root of 1 is 1. And we're using the point 4, 2. So its slope is going to be 2 minus 1 over 4 minus 1. So we get 1 over 3, so 1/3. And let's find the slope of point 2. Or not 2. The slope at x equals 3. So this is going to be 3 comma square root of 3. And again, 4, 2. So I'm going to have 2 minus root 3 over 4 minus 3. So it's 2 minus root 3. And the slope for 5, so again, that's 5 comma root 5. And then 4 comma 2. So it's going to be 2 minus root 5 over 4 minus 5. So 4 minus 5 is just negative 1, so it's going to reverse the numerator. It's going to be root 5 minus 2. The opposite of the numerator. You can find approximations for them, but we're actually just going to use those exact values there. Okay, so it says use the results to estimate the slope of the tangent line at 4, 2. All right, so what we've done is for 3, so between 3 and 4 we have that, and then between 5 and 4 we have this. Which two are the closest to the actual values? 3 and 5, right? So I would probably just ignore 1, and it's going to make it even more off, and I would probably like find the average of these two that are closest. So I'd find 3 and 5. So I'd do 2, my estimate. I'm going to have 2 minus root 3 plus root 5 minus 2 over 2. I'm taking the average, right? So root 5 minus root 3 over 2. So let's see what those are. So let's go ahead and, this one is 0.3 repeating, right? 2 minus root 3 is 0.2679, somewhere around there. Root 5 minus 2 is 0.2361, somewhere around there. So what we're doing is we're finding the two values between these, or we're finding the average of the two that were closest. So I'm guessing it's going to be somewhere between 0.26 and 0.23. All right, so square root of 5 minus square root of 3 divided by 2. So 0.252 is the approximation. All right, if I was actually, the actual answer, if we found it at that point, is 1/4. Okay, so pretty close. So pretty close. So how could you improve your approximations as well? Maybe you could take values that are even closer. So maybe you could do like at 2.04, so 4.1 or 3.9. That gets really close to that. All right, next up. Oh, yeah. Sometimes it's nice to see how they compare to one another in decimal form. Like I think in decimal form you could see that this and this were the ones you wanted to take the average of. This was much more. So it's somewhere between those two. You can tell like the actual slope. It's kind of, if I draw exaggerated, I think you guys will see. If you talk about the slope at 4, it looks like that. Before it, if you pick a point before it, it's a little bit steeper, I guess. So, and after it, it's a little bit less steep. You see what I'm saying? And then take the average to the average. Okay, let's go back to this one, and let's talk about why was this always 2 more? So why was your slope always 2 more? So let's think about a general point. So let's use 2, 4, and let's talk about the slope between x, x squared. All right, because any point on that curve is going to be in the form x, x squared. Make sense? All right, so if you talk about the slope between those 2 points, 2, 4, and x, x squared, you would have x squared minus 4 over x minus 2. What do you notice about that? The top is difference of squares, so you get x plus 2, x minus 2 over x minus 2. X minus 2 is cancel, so you get x plus 2. That's why the slope was always exactly 2 more than the x value. Okay, so those kinds of things are what we're going to see in chapter 2, which is the limit. So you're going to talk about what happens as you get closer and closer to a specific x value. So we were getting closer and closer to 2. Well, the slope is getting closer and closer to 4. So that's going to be what I'll look at. All right, so let me pass out your homework and you guys can get started on that.